So we're going to go ahead and collect the twos like we would in the lab. So if you right click on the panel, see how it says lower front panel? Now you can actually see inside the panel, and this looks very similar to what we would have if we were connecting it in the lab. We get this one here. We're also going to do the same thing over here. Now, and you can see these are pictures because they look like the same, but for whatever reason, LabBolt doesn't want to show the actual application. Now, all we need to do is drag a connection, which is our belt connection between the two. And you can see, why did that pop up? You can see when I move my mouse, it looks like a hand, and then when I go away. So if I drag my finger, oh, come on, sometimes they're not always the best. So when I dragged my finger at the right spot, I'm not sure why that keeps popping up. I have it going to hide, but it doesn't want to hide, so I'll move it over there. You'll notice now you can see what appears to be a belt connection between these two. Everybody see that? See the belt?
Yeah.
So essentially what this is, and this is in the real world, because these two things are, they're sort of just mounted next to each other, but this is just a rubber belt. It has teeth on it, but it needs to have some sort of tension associated with it. Otherwise, it'll just slip. So this is just a tensioner. You can see a small spring here. This is a bearing. It rotates in here, and then this just provides tension, just again like we do in the lab. There's nothing over here because you don't have any connection to the right of that. So you're only providing tension to the belt between these two. Once you're good with that, you're going to raise the panels, and you are mechanically connected. Now, the other thing I've got to do is I've got to run power to this unit to enable the indication of this. So I'm going to run my DC power over here. And now hopefully you can see that this unit is on. Let me move in just a little bit or zoom in. And you can see that this unit is turned on. Okay. We're going to run power. Takes DC input. It's a prime mover. We have it that way. And then it's hard to see, but we can have this as a prime mover or a dynamometer. A dynamometer is just a mechanical load. In this case, we're going to go ahead and actually have it provide some power. Now, the one thing that's really nice about this unit is you can actually get it to display a little more information. So why is this grayed out? I guess we have to provide more connections to it. So this is grayed out for some reason. Maybe we have to have the power on. Now you can see it's up to spinning. It's actually rotating and spinning. Okay, and it's going to spin up to a certain speed. And again, this is just for pictures to show the rotation, but you can actually control the speed here, and you can adjust. You should be able to adjust. That's the dynamometer. Why isn't this thing? Odd. Usually this is popped up, it would not be grayed out for me. Not sure why that's grayed out. You can also turn up the power and it'll slow down, or you can also lower, and I think you can stop it. Stop all that well. I'm not exactly sure why. Let me try reloading this because I should have this. This is my prime mover dynamometer. Do I have the wrong unit? Let me just double check. Yeah, I have the wrong unit. Sorry about that. I need this unit, the 4-quadrant one. This is the one that I actually want. This one is just a little bit more effective. So let's go ahead and power it up. And I'm going to turn the power on. And now you see I turn my power on. You can see this is grayed on or off. You can go ahead and you can click over here and you can actually display information about the device that you're trying to configure. So I want the 4-quadrant, not the 2-quadrant prime mover. That one doesn't have the effectiveness. Now this one, if you read the functionality, we're going to set it up as a clockwise prime mover break. And we can actually go ahead and get it to start spinning. We can start stop, we can turn it up. And we can just increase the speed as much as we need to. So you can see it spinning up. And now we're at 1016 RPM. You can see the speed here. This is where we can get much better control over it. So eventually we're going to run this to 1800 RPM. This is how we're going to play with this unit. Okay. So this is the capability of it. You have the meters here. You can display. There's no torque. There's no power. There's energy. That's electrical energy going in. So it's not a huge deal in terms of getting it set up. We're really just interested in the speed, and then we'll use other parameters to monitor it. So I'm going to stop that. Okay. I'm not sure why it says 1933 RPM, but whatever. Now, a couple things. Okay. So we're going to use this as a dynamometer. So a prime mover. So a couple things on this. If I zoom way in, and again, this is just a recommendation. You can see that there are some analog outputs here. So I could actually run the torque output and the speed output. I could actually have those being monitored by my analog inputs over here. And if you look, channel 7 is already configured for analog. So I'm going to run my torque to channel 7 and my speed to channel 8. Now, one thing that when we work with analog, these are data acquisition devices. They provide information. So this analog device over here has to have a common ground between these two. So, excuse me, I'm still dealing with a cold, so I apologize for coughing as much as I do. Okay, so I've got this configured. This unit is set up. I'm good to go for going on for my dynamometer configuration. Okay, so I'll give you a couple moments to go ahead and set that up so that you can monitor that. We'll also take a look where we can enable our speed. So I'm going to turn on, if you look over here, this is analog input 7 for torque, analog input 8 for Newton meter. I'm going to go ahead and turn that up. Again, it's just much easier to do it over here. Turn it up. It's going to try to go to 1800 RPM. If I look back at my meter and turn on the refresh, you can see the speed here, 1797, 1797. So why am I telling you to do this? Because this information is the same. Well, we're going to be doing some data recording and some tables where you're going to be plotting speed versus voltage characteristics. I'm going to try to have you all set it up so that you have all this information ready to be reported in a data table. Whereas if you don't have this information provided over here, you're actually going to have to enter it in manually. Okay. So that's just a suggestion to go ahead and set it up so that you can automate processing the data. All right. So I said I was going to shut up for a moment to give you everybody caught up. So let me give you one moment and I'll get a drink of water here. And then we'll get started with the lab. Do people want to be put into their individual work groups?
Yeah, I feel like that'd be beneficial.
Okay. All right. Let me go ahead and I'm going to have, we have 5 groups that are active. So let me set up breakout rooms. I'm going to do 5 and I will let you all choose your room. So I just need one person from each group and you can decide to pick a room. And then your other partners will join. So that, so the 5 that are going to be running the software, go ahead and join a vacant room. And then your other partners will go ahead and join in. And then I can go ahead and jump in at any point in time as well. So here we go. Okay, you should be able to jump into the room that you want. So Matt's in room 1, Jake's in room 3. Aiden's in 4. Lions in room 2. And Austin in 5. Okay, hopefully you all can hear me. And when you're ready, you'll just jump back into the main room when you've set up your circuit. So you can go ahead, and I'm going to jump into each room individually. And when you're done, you can just jump back into the main room. So here we go.
Hey, Paul,
Yes.
is there a way you can like is there a way we can share screens inside the breakout rooms? Because it's not letting us currently.
You should be able to do it now, but let me go in and I'll jump into your breakout room. How's that?
All right.
Okay. Still waiting for a couple of people to join the main room. Okay. Everybody should be in the main room. Good. And your rooms, you don't have to do anything. I'll just open all the rooms back up. But this is just the way that I can get everybody to come back into the main room at once, okay? So let me share my screen and get started with the lab. Okay, so now we're going to go ahead and we're just going to configure it in part or figure 2 of the winding. So I'm going to run my DC current, right? So my DC current is going to run through winding 3. So let me move this out of the way so I can see. So DC current is going to go through I3. So I'm running from here into my field winding. I'm going to cheat this over a little bit. So I went out of the plus into I3, continuing on into the DC, which is terminal 7. And then I have to run from terminal 7 over to neutral. And now I have basically just completed where I can monitor my DC field current through winding I3. Okay. The next thing I'm going to do is I'm going to connect the synchronous machine in a Y winding. So this connects here. This connects here. And now I'm going to run the individual phases. E1 is going to be just my phase 1. And that goes from here to neutral. E2 is going to be phase B to neutral. And E3 is going to be phase C to neutral. Okay. So you will notice that all I have going from my machine is I've got DC power over here and DC power over here. I have no AC connections in any way, shape, or form that are connecting to this machine. But what we're going to see when we do the data acquisition and we look at some of the waveforms, we're actually going to see how we're going to produce an AC output, a 3-phase output based on monitoring these individual voltages. Okay. All right. So I'm going to go ahead and set up my metering. So I have my torque, which I'm not going to use because I'm not really measuring torque. I'm going to have my 3 voltages that are AC, and then I'm going to have my I3, which is my current, and that has to be a DC value. So if you're going to be monitoring these parameters, remember that these has to be a DC because your field current in a synchronous machine, and that's the key thing about a synchronous machine, it's at a fixed value. It is not AC, which can provide some rotation. We learned that when we looked at 3-phase, excuse me. Still dealing with this nasty cold. Hold on.
Hey, Paul, we have a question here.
Yes.
Is there any way that you can like, I don't know, in the software, if you can like clean up how the wires are, but like, it's kind of a struggle to follow everything that you have there.
You can't
They
really
kind of blend
clean it up.
together.
You can color code things a little bit, but that is the problem with the software. It's just like when you guys asked me to check the labs, it's the same thing. This is just how, you know, if we could train the wires a little bit, we can see it that way, but you can see that I have these going in this direction. I can try to make these bluer.
Yeah, that helps actually a lot.
Yep. Okay.
Thanks.
Sure. Let me just do this last one. Let's pick. It's green, close to green. Okay. And then my DC current is going to be running through here. So try to pick that up a little bit so you can see it. And go from there. You can also mark up or append the figures. And you can do that on the handout. Okay. So I'm ready. So I'm going to flip my DC power because I need my field current. I'm going to look at my dynamometer. I'm going to start it, get it spinning up to 18 or so 100 RPM. And is this not connected? Hold on. Did it lose its connection? Did I turn the power off? I guess I. Stop it this way. I thought I stopped it. You can see the software is not the best. It's got some bugs. All right, somehow it seems to have not lost that connection. Okay, so let's flip the switch, power this up and rotate it. Now both are spinning. And a couple things. So you can see it's a little bit slower. So let's increase the speed, get it as close as we reasonably can to 1800. We'll overshoot there. And you'll notice that this knob is different because it's trying to control what would be the no load speed. So that's why one of the groups, when I was in their breakout room, they said, why don't I just set it like this? You can see 1963 to get 1800 RPM because it doesn't actually know the speed. It's not a closed loop control mechanism. All right, so now let's go over to our voltages and we'll do continuous refresh. And you can see nothing's happening. Look at our voltages, they're all zero. Our current zero, our speed is 1800 RPM. If we take a look at our, actually, let's not go here. Let's go with our oscilloscope and let's make channel 2, E1, channel 3, E2. And channel 4, E3, and turn on my refresh. Why am I not getting any voltages there? Anybody want to guess as to what the problem is? Spinning. This power supply is turned on. Why am I not getting any voltage? How about the switch? Isn't this an open switch? So the switch is open, so there's no DC current going into the field. And that field is what is responsible for going ahead and setting up our excitation. So if I flip the switch, look at my voltages now. Now I'm actually getting voltages. And compare that to here, and you can see I'm getting 101, 102, give or take volts, and then also look at my current. It's 467 milliamps DC. Okay. All right, so my waveforms, you can see they're around 60 hertz or a little higher. I'm getting an RMS value. That's okay. And let's see. I guess that they're going to just bounce around, so that's fine. If I want to stop it from bouncing around, I can go ahead and use that. But you can see that they all look about 120 degrees apart because this one repeats every 360 degrees, and then it breaks it up into thirds. So the question is, observe the waveforms and induced across the stator, are the waveforms sinusoidal? Is the answer to that, are they sinusoidal? They're only sinusoidal because we actually turned on the switch. But beforehand, they were not, right? They were giving us some wonky results. So yeah, they look pretty sinusoidal. And again, that has to do with the construction of the synchronous generator. The way that it is configured actually produces the 60 hertz output. So now what I'm going to do is I'm going to tweak this a little bit, and I want to get 120 volts here. And I want to get 1820 RPM. So let's bring this back up and let me adjust this down a little bit to get at 1800 RPM or as close as I can. Okay, that's pretty good. Now, let's bring up my voltages. And I want to get this to 120 volts. Each of those are approximately 120 volts. How do you suppose I can get 120 volts here? Chris, you had a good question for clarification. You have any idea how I could get 120 volts for E1, E2, or E3?
Honestly, not exactly. We're still trying to figure out some of our stuff on our end, like actually getting the machine to work.
Okay. How about Sean? Mr. Mishu, you have an idea how we could get that to 120?
No, I don't.
Okay. So one of the things we talked about in class before I had to do some remote classes, some pre-recorded classes, is EA equals K times phi times omega. K is a constant. Omega is a constant. We're at 1800 RPM. The only thing that we can change is phi. So how do we increase the magnetic field strength? We put more DC current. So watch as I change this exciter. Look what happens to this current and look what happens to the voltages. So I increased it. Voltage goes up. Now I'm at 0.5. Let's go up a little higher. So I'm going to go ahead and shrink it down so I can have these on at the same time. Okay, so I was at 3.3 something. Now I'm at 0.55 and the voltages have increased. So I'm going to continue to increase these until I get 120 volts. Oops, wrong one. I'm going to go over a little more. Sorry about that. Okay, 120, but notice the speed changed a little bit. It was at 18.1, now it's 17.99. That's because the mechanical system has to work a little harder because you get some magnetizing having in there. It actually looks like a little bit more of an induced load. So let's see if I can tweak this just ever so slightly and get that back to 1800 RPM. Okay, so now the thing we'll go back to is we'll check the waveforms and we'll look and see. They're the same. They're all sinusoidal. But now that what we see is that they're spaced by 120 degrees and the magnitude is increased. Let's see if I can change the time base here. Let's see. Let's make that a little bit. It'll move a little bit, but you can go ahead and check to see if those are 120 degrees. Okay. All right, so we get pretty good waveforms. They're pretty good sinusoidal. So the question for the lab number, for part number, let's see, what part is that? Number 6 is, are these waveforms sinusoidal? Well, what do you think? Do they look like good sine waves here? They look pretty good to me, so I would say yes. They are pretty good. Now, what is the phase shift between each of them? If you're not sure, you can always drag cursors and you can go here and here, and these look like they're about at the peak. And you can see the difference between this channel, which is this sort of this reddish pinkish channel, and then this channel. You can see the difference between the two is let's see, cursor 1, cursor 2. The difference is 254.61. That's in seconds. Anybody know how to 5.58. Anybody know how to convert that to actual time or degrees? How many milliseconds in one cycle for 60 hertz? 1/60 is 16.67 milliseconds, right? You can see the frequency is about 60 hertz. The time difference here is 15.58. So 5.58 divided by 60 gives you about a third, correct? Give or take. And if I realize that it takes 360 degrees to do one full cycle, a third of that value, and let me see if I can bring that up in MATLAB real quick. So let's do 5.58 divided by 16.67 milliseconds, which is the same thing as 60, is 0.093. I multiply that by 360. Oh, wait a minute, sorry. I don't have that correct. So 1 divided by 60. So my time, I'll just put this in this way. Time base is equal to 1 divided by 60. It's 16.67 milliseconds for that value. So if I take my 5.58 milliseconds, because this is in milliseconds, you can see that over here, it says milliseconds. And then I divide that by my time base, I get. Oh, there's the lowercase b. 0.32448. Now I multiply that by 360 degrees is 120.53 degrees. So each one of those is about 120 degrees of electrical separation between them, because you can see that this distance here to here is essentially the same as this distance. We can try it. We'll drag this one over and see if we still get 5.58 or approximately 5.58. That looks pretty close to the peak. Yeah, 5.54 versus 5.58. So the electrical separation is about 120 degrees. Okay. Questions? Okay, no questions. So what happens, what do you think will happen in step 7 when I change the speed to 1,000 RPM? What's going to happen? What do you think? How about Austin?
I'm gonna be honest, I'm still messing around with this software, trying to get it to read and measure values.
Okay. Is it not connecting properly, or?
I mean, I think I have everything hooked up properly, but clearly I don't, because when I turn the power switch on, nothing's working.
Okay. Well, why don't we do this? I'll take a pause from my discussion, and then I'll jump in and I'll help those guys, and then we can get back to this part. Okay. So why don't you go ahead and let me set up your breakout rooms. And you all can jump in your breakout rooms, and I will help Austin's group go ahead and get started. So go ahead and jump in your breakout rooms, and I'll make sure everybody's connected.
We might need some help too.
I'll jump into everybody's room.
Awesome, cool.
Everyone else was in breakout rooms.
Sorry, guys, there was one question in the breakout room, so I'll be right there. Hold on. Okay, guys, I'm back. Sorry about that. All right, so while people are jumping in, we can think a little bit about what happens in step 7 when we take it down to 1,000 RPM. What do you think happens? I'm going to decrease my speed to 1,000 RPM. How does that work? Anybody? There's two things that are going to happen. Remember, the speed of rotation determines the frequency. So if it takes 1,800 RPM to give me 60 hertz, I'm going to go down to 1,000 RPM, and
Would
I'm
it
going
like
to
change the amplitude? of
It's
the
going to do two things,
oscillation?
right? It's going to change the frequency, and it's also going to affect the amplitude because it's EA equals K phi omega. So because my omega has decreased, my radians per second or RPM has decreased, the output's going to drop. So my frequency is going to go down as indicated here, and then you're going to see these magnitudes drop. So let's go ahead and drop that to 1,500 or 1,000, I'm sorry.
We can't see your screen.
Oh, I'm not sharing it. Sorry about that. Bring it up again. That's right, because whenever we do breakout rooms and I join. Okay, so let me go back to 1,800 RPM or thereabouts. Okay, so you can see my frequency is around 60 hertz. The magnitudes are all around 120. They're bouncing a little bit, but that's okay. Now I'm going to drop it to 1,000. And you can see the amplitudes are dropping, but also the waveforms are elongating. That's because the frequency is dropping, but the elongation, but also the amplitude reduction is because EA K phi omega is dropping. So now look at my voltages in the 60s and 70s. So much reduced. So the question is, for step 7, how do the amplitude and frequency vary with the speed of the synchronous generators decrease? Well, the amplitude is decreased because that EA equals K phi omega, and the frequency is decreased because if you go back to our discussion when we were just looking at rotating MMFs, we determined that synchronous speed was, what was it, 60 or 3,600 divided by the number of pole pairs. Well, that was for 60 hertz operation. If we're down at 1,000 RPM, we're going to get a much lower frequency. So this one is actually showing no frequency. Anybody want to guess as to why it shows no frequency? See how good you are with looking at oscilloscopes. It's a time base, right? It needs to know, it has to have a couple of zero crossings. Right now, I only have 1. So if I change this to 5 milliseconds, I'll have 2, and now I can get my frequency. So it's not all the way down to 30 hertz, because that would be half the frequency. 1,800 to 900 would be 50 hertz, or I'm sorry, 50% of the frequency would be 30 hertz. I'm slightly above that. So that's how it answers that question. Okay. Question on that? Okay. So did the 120 degrees change at all? Well, let's take a peek. Are we still 120 degrees out of phase? Well, now the difference in time is 9.93. But remember what my frequency is, it's 33.5. So my time base, do that again. My time base is no longer 1/60, it's 1/33.52. And now my time to figure that out. So I'm going to go 9.93 milliseconds divided by my time base is the same number, right? As we had before, pretty much the same number. So then if I take my answer and multiply that by 360 degrees, I get about 120 degrees. So it still is a balanced machine because that has to do with the physical construction of the machine. The windings are all the same and they're all spaced approximately the same. So you can actually take a 60 hertz generator and take it over to Europe and run it at a slower speed, and it'll be happy to produce 50 hertz. Transformers are a little bit different, but generators, you can have 50 hertz operation or 60 hertz operation without any issue. There may be a slight difference in cooling, so you might not be able to put out as much output, but a 60 hertz generator can usually work perfectly fine in 50 hertz. Okay. All right, so now let's go ahead and slowly turn the exciter. So we're not changing the speed, we'll keep it there. We're going to bring up our lab and we're going to change the exciter. And we're going to go ahead and we're going to rotate it counterclockwise to decrease the field current. What do you think is going to happen to the waveforms? Decrease the excitation. What is that equivalent to in that EA equals K P omega equation? How about Eric? You have an answer?
So change the amplitude.
Yeah, it just changes phi, right? So as I change this, I decrease this, all you're going to see is a reduction in the amplitude. The frequency is not going to be impacted. So lower it, lower it, lower it, lower it, lower it. Turn this back on. And notice the frequency didn't change, but I went from almost 70 down to lower values. And you can see the frequency is slightly changing. That in the real world wouldn't necessarily happen, but my amplitude changes. So this is actually how you operate real-world synchronous generators. You're adjusting this excitation because the voltage on the terminals of the machine is being impacted by what's happening in the grid. So this would be part of what's called your governor control, your excitation controls, where it's maintaining a constant voltage on the terminals of the machine. What controls the speed, that would be the governor, and that is actually going to try to be responsible for maintaining 1800 RPM because we're trying to put out 60 hertz and we're trying to put out nominal voltage. So in a real world synchronous generator application, you have two separate controllers, governor for speed control and excitation system for voltage control. And we'll get more into the actual details of that probably next semester, but this is exactly how real world synchronous machines are operated. We just would go ahead and use slightly different characteristics. Okay. So questions on this part? Because now I'm going to turn that off. I'm going to stop it. And move on to step 9. The only thing I'm going to do in step 9 is this field current here. Instead of going into the case, I'm just going to go ahead and run it in here. And then I'm also going to delete some of these wires just because it makes it a little less messy. So I'm deleting those. Now I only have E1, but E1 is going to measure across 2 phases. So I'm connecting over here. Notice that I'm still going to maintain my Y connection over here because I still have to reference it as either a Y or delta. But now I'm going to be measuring across 2 voltages here. So basically, I'm looking at the line-to-line voltage on the output of the generator. And now my current, my field current has to go through all my resistors. And I'm going to go ahead and I'm going to connect this field current and I'm going to make it so that I've got all possible connections. So let's see. Let's put these in series to start. Let's put them in series. So I'm going to run my current through here, and then here to here, and here to here. And we're going to be changing that a little bit, just depending on what's going on. So we'll put these 3 switches in here, and then see what we can get for current values. So I'm basically saying it so that my DC current now has to run through here, and then continue into this device, run through this 300 ohm resistor, another 300 ohm resistor in series, another 300 ohm resistor that's in series, and then I'm going to run that into the terminals of my generator, and I'm going to see if I can go ahead and get my values set up. Okay. I'm actually going to start off with one of those switch opens because I want to go ahead And I want to look at it under no load conditions, essentially no excitation. And so this is where it would make a lot of sense to go ahead and set up this here. So I only want E1 and E2. I want excitation. I'm going to go ahead and include speed. And that's it. Let's see, voltage. Oh, I have field current. Oh, and one other thing I can include too, you don't have to do this, but I also can include frequency. So let's see, I guess I will put this one over here for frequency. And I'll just change the frequency. Okay, so I'm gonna have a curve where I'm measuring voltage, frequency, field current, and speed. And so now I'm gonna go ahead and set up my data table so I can measure those parameters. All right, so let's go ahead and set my columns. So I have, oops, I gotta turn off this one. Sorry about that. For some reason, if you have on your oscilloscope, it gets confused as to what you're trying to do. Well, let's try that again. I want here, I thought I had speed. Is my speed not on? Let me double check and see. I have speed. Why is it giving me torque? Usually it would be blacked out, but that's okay. It doesn't want to do it. So I have voltage, magnitude, frequency. I want my current and here. And those are my values that I'm going to go ahead and do. So this is how I'm setting up to do my first application. Now I'm going to go ahead and I'm going to start my machine spinning. So bring it up. And one of the student groups actually said, if you do this for constant speed, it'll actually self-control. So you can set this up at 1800 RPM and it'll adjust itself. So if you don't want to keep tweaking it, you can go ahead and specify that way and it'll automatically control to 1800 RPM. Or it should. Now it overshot. Now it's spinning down, getting closer and closer. So regardless of the load, you should be able to get that set up. Okay. So now I'm going to go ahead and look at my meters. So I will shrink this down and bring up my metering window. And everything is all set. So I've got let's toggle on my DC. I've got my initial value. This should be collecting it up. So this is when it's going to be getting close to 1800 RPM. Now I'm going to bring up my metering window and I'm going to record because my field current is at 0 amps. My speed is 1800. My voltage and my frequency are both 0. And the reason why they're both 0 is because my excitation is not on. I don't have any resistors in here. That's this resistor is in the open position. So I have no current flow. Now I'm going to go ahead and I'm going to measure this value here, and I'm going to go and flip on my switch. And I'm going to check to see, I needed to go between 0 and 450 milliamps. Okay. So I want to go ahead and see if I can turn this down. So let's see if I can bring this all the way down and get to 450 or 0.45. I can't get there from here. So instead of this 300, I'm going to put a 1200 in here. That's pretty good, right? So I'm getting close. So let's see if I can put another 1200 in here. Almost there. If I can max this out. That is maxed out. And I want to be at 0.45. So let's see if I can toggle this one on. And I'm a little under, so now I'm going to reduce it. Get that to 0.45. No, it doesn't want to do it, so I'm going to have to toggle this one and do this one. Let's see. There we go. So now I have my 0.045 milliamps at 1800 RPM. Notice that the voltage and frequency are still 0. Anybody want to guess as to why those are both 0? Because there isn't sufficient magnetic field in this machine to produce a voltage. It's only when I start to crank it up. Now you can see I've got more than the 450. So then I would go ahead and actually get some voltages here. So I'm going to bring this one back, get it down to 0.45 like I had. And now I'm gonna go ahead and record this in my data table. So that's my second step. I'll do one more and I'll give everybody the chance to go ahead and do the last little bit. So now I've got to go to 0.09. So let's see, let's take this one off and put this one up. Let's do the same thing here. And let's see if I can. Wrong way. Not quite. So let's see if I can. Get that from here. No. So let's see. I'll put these two in parallel. So this is kind of like a binary choice where you're trying to figure out, how can I get to the value that I want. So let me go ahead and shrink this because it's kind of a pain. So I'm almost right there with this value here. Let's see, can I adjust it? I think this is just going to increase it. So I've got a 300, a 300, and a 600. If I put this one on, no, that's too much. Get that from here. So let's see. So I can't get them with these two in this. So here's the best case. So this is the data we'll record. So instead of 90, we'll go to 0.098. There is a way to get to 90, but I don't want you to go ahead and spend all day reconfiguring your circuits. So at this point, I'm going to record this data point. Okay. All right, now it's your turn. Go ahead and fill out the table that is required for step 13. And then we'll go ahead and I'll launch your breakout rooms. And that way you can go ahead and get started. And I'll ask, or is there any questions right now before I set you up in your own breakout rooms? Questions?
Yeah, just on the 450, is that just a function of that particular generator? Or?
Yeah, so you can go a little bit higher, but 450 is a good stopping point. I can't remember the voltage. I think at 450, you get about rated voltage.
Okay.
Maybe a little bit below. Okay. All right, let's go ahead and launch the rooms. Okay, the last part of the lab, excuse me, is just basically to put the maximum level of excitation that you can. So you can either short out the resistors by putting jumper wires in. The other thing you can do, right, is this is going from here to here. I'm going to delete this wire. And I'm going to take this wire here and move it right into terminal 7. And then I'm going to look at my metering. Going to turn this up maximum field current I can get. And the voltage is 230, whatever. And my frequency is again about 60 hertz. So you're going to do the 450 milliseconds, and then you're going to jump up, or 4 milliseconds, 450 milliamps. And then you're going to jump up to the maximum you can, which is in this case, in my case, it's 877 milliamps. And I plotted all those data. I'm going to go ahead and share my other screen. And here's the data that I took. The end of 15. And if you look, 15 and 16 was the one where I included the frequencies, but it doesn't change. It's always going to be 60 hertz or thereabouts. So it makes it a little bit easier, but some variability. So here's my data table with the voltages, the frequencies. And the first two, there's no frequency because there's no voltage. The field current, IF, and then my speed. Those are the values. And you can see I wasn't really all that particular when I got to these three, but then I was much better about maintaining it. And then I recorded. And so your frequency is 60 hertz. That's what you measure. And then if you did the 1800 RPM divided by 60, and there are 4 poles or 2 pole pairs, 1800 divided by 60 multiplied by 4/2 gives me 60 hertz. And then here are my plots. I just did these in Excel because it's much easier. So let me bring up my Excel file. And let's see. Let's do it this way. And I'll open it. And I will go synchronous generator lab. So I just copied my data. So here's my voltage, frequency, and my current. I have those values here. Here's voltage versus field current. I have those values here. Then I also did the one, so I'm just showing you my data. This is voltage versus speed. So I did my varying from 200 to 2000. Okay. So I have voltage versus speed and frequency versus speed plots. So that one I probably should have done a little bit better job of explaining. Step 21, but I don't want to take too much time. But essentially what I did is let's do this one. Let's pause here for a second and let's do 21. So any questions up until 21 before you see the curve parts that I did here? Any questions? Okay. All right. So I'm going to go ahead and excuse me. Share screen 1, and I'm going to see if I can get 300 milliamps or so of field current. So let's bring this up, and I'm way high. Turn that all the way down. I know that's not going to work for me. So now I got to start switching back in my resistors. So I'm going to disconnect this here and run that over here. And then this one I'm going to run over here. And then I'm just going to tweak it and see if I can get to 300. Let's see. So it's 0.908 or 0.098. Let's see if I can get 300 by turning this one up. I'm not going to get there from here. So let's switch that one in. Oops, I want to go the other way. And so now having these 300 ohm resistors, you can see if I've got a bunch of 300 ohm resistors here, my current. Why'd my DC current go to 0? Are they all open? Oh, right here, you can see that I can't get there from here, right? So I can start putting a bunch of these in parallel and see if that's going to get me there. I got my 3 resistors in parallel, so I'm getting closer. But I'm not there yet, right? You can see that I'm not there yet. So here's another option you can do. Or what if you want to do, if you want to continue to increase the current, what can I do for this one to make it so that I don't have this resistance in here? Well, I'll delete this wire. And I'm just going to connect over here because now I've taken out this resistance here. Now I'm closer, right? You can see that I'm pretty darn close. I'm not at 300, I'm getting close. And remember, if I lower this down, it's going to lower this value. So I'll delete this wire. Doesn't want to delete it. And I'll run this one over here. And now I'm at 400. So let's see, can I adjust this to get to 300? Am I getting there? Am I going to make it? Not quite. So I'm going to take the 600 and see if I can get there from here. And I can get to 300 right there. So it's just basically kind of tweaking some of the values to get to what I need. Okay. So I have 300 milliamps here. And the way that I did is I just had a 1200 ohm in parallel with a 300 ohm, and I'm somewhere in the middle in there. And now I'm going to adjust my speed and I'm going to go up from 200 and go up to 2000. So I do my 200 here and wait till it settles. And in this case, all I need is I need a plot of voltage versus speed and frequency versus speed. So I'm going to go back to my data table here, and I'm going to clear all these out. And all I need is my voltage. I need my frequency, and I don't need my current. So I hit apply. Now these are the only values that I'm interested in. I've got 200 RPM, so I'm going to record. I'm going to change it to 400 RPM. When that stabilizes out, I'm going to hit record. I think we stabilize, so I hit record. And then on and on and on and on. 600. If I can move this down a little bit so I can see it at the same time. Oh, why did we do it over here? Okay. All right, so I'll let you all finish that one, and then we can look at the plots. Any questions before I open up the break rooms again? But I think this will be the last time we go separate break rooms, because then we're at the end of lab.
What step are we on? Because just we kind of got turned around with some of the stuff, trying to figure everything out.
Yep, this is step number 21. Actually, we technically
Okay.
started off on 20, and we're doing 20, 21, and 22.
Okay. All right, thank you.
Yep. All right, I'll open up the break rooms and I will check in.